Welcome, everyone. Today we're diving into a breakthrough in AI performance, KernelSkill, a multi-agent framework designed specifically for GPU kernel optimization. Instead of relying on the opaque guesswork of standard large language models, KernelSkill introduces an explicit dual-level memory architecture. Our target? Unlocking the maximum hardware throughput for AI operators. Our method? A closed-loop system driven by externalized expert knowledge. And the result is a perfect 100% success rate on KernelBench with up to 5.44x speedups. Let's start with the big picture. Look at the modern AI stack. Mainstream frameworks like PyTorch and Hugging Face are incredibly powerful, but their high-level efficiency entirely inherits the efficiency of the underlying GPU kernels, things like gems, convolutions, and data movement. The reality is that expert-driven kernel tuning is a highly manual, costly, and slow bottleneck. It requires profiling-guided iteration, deep hardware awareness, and highly specific instruction choices. So, why not just use LLMs to automate this? Well, current automated LLMs give us the illusion of refinement. As you can see on the left, they fail in real-world environments because they rely on internal, opaque heuristics. They lack historical state and explicit rules, meaning they waste computational budgets on low-yield directions. The chart on the right shows the consequence. Performance metrics wildly oscillate due to mismatched strategies and zero traceability. Here's how kernel optimization intelligence has evolved. We've moved from the extreme cost of manual tuning, to high-cost training-based LLMs, to agentic LLMs that still struggle with weak interpretability and oscillating stability. KernelSkill is the new paradigm. It introduces dual memory tracking to maintain both context and expert knowledge, operates with zero training cost, is 100% traceable, and consistently achieves a 100% success rate with high performance. The core insight driving KernelSkill is externalizing expertise. We are taking those model internal heuristics, the implicit guesses, and replacing them with traceable, trajectory-aware structured skills. By using a two-level memory system, KernelSkill effectively decouples optimization knowledge from LLM inference. This architecture ensures stability and makes every single optimization decision fully auditable. Let's look under the hood. KernelSkill is a closed-loop expert system. It starts with a PyTorch reference, which goes to a generator and then to a reviewer. If the code passes compilation and verification, it moves to the optimization stage, utilizing a planner with short-term and long-term memory. If it fails, a diagnoser steps in, uses a short-term repair memory, and hands it off to a repairer. It's a continuous, data-driven feedback loop. But how does the system know exactly what to optimize? By grounding agent actions in diagnostic reality. Relying on profiling alone isn't enough, we need deep structural awareness of the code before attempting edits. We use a profiler for real-time execution data, but we pair it with a feature extractor that captures rule-based and LLM-based structural features. Finally, the compiler and verifier act as correctness validation gates. Now, let's talk about the brain of the system. Memory level 1 is our reusable knowledge vault. This is where we ensure zero hallucination and 100% traceability. Raw profiling data is strictly filtered through metric normalization, bottleneck gating, and decision table mapping. Every single optimization method is selected via strict deterministic gating, not LLM guessing, and is backed by concrete cues derived from expert GPU literature. Memory level 2 is our short-term memory, ensuring trajectory-aware iteration. In the repair stage, it tracks cyclic compilation failures to break the cycle and prevent getting stuck in infinite fix loops. In the optimization stage, it tracks per-task history to prevent repetitive backtracking. A new base kernel is only promoted if it hits strict speedup thresholds, guaranteeing monotonic, stable gains. Who executes all of this? Our multi-agent execution cast. We have the generator drafting the initial implementation. The diagnoser analyzing logs for a history-aware repair strategy. The repairer executing precise code edits. The planner synthesizing long-term rules with short-term data to formulate the next strategic step. And the optimizer assembling the gear, implementing the strategy while adhering strictly to formatting constraints. Let's look at a real-world case study. Without memory, a standard LLM fixates on simple operator fusion but leaves the heavy GEMM computation as a naive loop, resulting in a miserable 0.032x speedup and wasted iterations. With KernelSkill, the planner queries the long-term memory, accurately identifies the dominant GEMM bottleneck, and applies shared memory tiling and vectorized loads. The result is a massive efficiency gain. The results speak for themselves. On KernelBench, KernelSkill achieved unprecedented effectiveness. Evaluated over 250 tasks, it is the only framework to maintain perfect correctness with a 100% success rate while pushing kernels significantly closer to theoretical hardware limits. We achieved average speedups of 5.44x on level 1, 2.82x on level 2, and 1.92x on level 3 compared to Torch Eager. Are both memories really necessary? Absolutely. KernelSkill achieves higher final speedups in just 15 rounds than baselines do in 30. Our ablation study shows that if you remove the short-term memory, the system loses stability and the success rate drops. If you remove the long-term memory, the speedup is neutered, plummeting from 5.44x to 1.77x. Trajectory tracking provides stability, while externalized knowledge provides speed. To wrap up, KernelSkill represents the blueprint for AI code generation. The paradigm shift is clear. The path forward is not just larger base models or more trial-and-error compute. The new standard demands explicit externalization of expert knowledge coupled with rigorous state tracking. The result? Robust, feedback-driven, and highly interpretable GPU kernel optimization. Thank you for your time.